very much for the invitation. It's a pleasure to speak here. So I gave some short talk at the beginning of the semester when I came. This will in some sense be a continuation and slight diversion from that talk. So let me just remind everybody here, all of you know them, but let's just write the Euler equations for a perfect fluid, so inviscid and incompressible. We're thinking of two dimensions, and for simplicity, let's think of bounded planar domains M with boundary, say, partial M. And the fluid is confined to here. So at every point, there's an associated fluid parcel, and that's moving with some velocity vector field, u, x, t. Okay. And on the boundary, the fluid is tangent. So if let's call n the outer normal, then u dot n is 0 on the boundary. And this velocity evolves according to the Euler equations, which say that the Lagrangian acceleration is equal to a gradient of a pressure. And along the while, the fluid maintains incompressibility, which is just the condition that the divergence is 0. So okay, the pressure is, of course, determined to enforce this over time. So being in two dimensions, this condition right here, together with some sort of mild regularity, ensures the existence of a string function, which is a scalar function representing the Hamiltonian for the velocity at every instant in time. So namely, u is written as the skew gradient of stream for each time. And the significance of this function is that level sets of the stream function are streamlines, hence the name. So if I look at psi equals a constant, that level, the velocity by construction is tangent to this. Another very important quantity in two dimensions is the curl. So planar fluid, if you regard it as symmetric in the z direction, then the curl is out of the page in just one component. So that object, omega, is the perpendicular divergence, if you like, of u, or with this notation, the Laplacian of stream. And the point about this quantity is that it's transported by the Euler equation. So we can write a vorticity formulation which is that the vorticity is transported as a scalar field, and the velocity is recovered from the vorticity by some non-local operation called the Biot-Savart law. And this is the, say, Dirichlet Laplacian, so that the velocity is tangent to the boundary. Okay, so this is some transport equation, nonlinear, non-local transport equation that completely characterizes incompressible fluid motion in this context. So we can really just think of the vorticity as being our defining variable of the fluid. So we're interested, broadly speaking, in the behavior of this system. It's an interesting question because this system has sort of no parameters, no natural parameters, no imposed structure. It's just free motion of the fluid. You can think of it as energy minimizing paths between states of diffeomorphisms representing the particle configuration. It's really sort of a universal type free model. And you want to know what happens over long times in general. And the first thing that you want to think about when you study the long time behavior are just the invariants of the motion, the first integrals, if you like, of the Euler equation, of which there are some known classes. Okay, so let's begin by momentum. This is an invariant that depends somewhat sensitively on the domain, the vessel of the fluid. So if you have the two torus, it's not really of this type, but the two torus, the entire integral of u, which is the momentum, you think of the density as unit, is conserved. Similar invariant is true on the channel where you only have one component, the horizontal component of U. And on the disk, you have angular momentum as its analog. But in general domains, this invariant is broken. So you don't have this information. Okay. Another much more robust invariant in many ways is energy. And that's just 1/2 the integral of U squared. The kinetic energy integrated in space is conserved. This is true just using incompressibility and the fact that the velocity is tangent to the boundary. So it holds on any of these domains. And finally, another fairly robust invariant are the Casimirs. This is true on any domain also, and it's just that the integral of a continuous function of the vorticity integrated over the domain is preserved. This one follows from the fact that being a transport equation, you can write the vorticity at a later time as the initial vorticity composed with the inverse Lagrangian flow map, namely the map that sends particles at an initial time to their later positions via motion along the velocity field U. So what this is telling you is, well, first of all, because U is divergence free, this map preserves area, which is an area preserving diffeomorphism from the domain to itself. Particles on the boundary stay on the boundary because U is tangent to the boundary. And it's telling you that omega of t generally lies in the orbit of its initial data, omega 0, in the group of area preserving diffeomorphisms. So in particular, this orbit, let's just define it to be the collection of all omega, such that omega can be written as omega 0 composed with some volume preserving diffeomorphism. The fact that it's volume preserving means that when I take functions of that thing and I integrate over space, since the Jacobian is 1, I get that this is preserved. It's just equal to the initial data, the integral of the initial data. These invariants are, again, completely robust to changing the domain. They are a little bit more fragile than the energy in a sense that I'll discuss later. Okay, so as a consequence of these invariants, essentially, we have the following classical theorem by, for example, Holder and Boldinger, which is well-posedness of this system for vorticity, which is C alpha. So for any alpha bigger than 0 and omega 0 in C alpha, there exists a unique omega in C alpha spacetime, which is a solution of the Euler equation. Okay, furthermore, we can bound the C alpha norm by its initial data. Up to a double exponentially in time. Okay, so we have an estimate of the solution in this space that says it can be at most as big as this factor, which grows double exponentially in time and degenerates when you send alpha to 0. So this is what this theorem is telling you, is that Euler is a perfectly well-defined dynamical system on the space C alpha, so namely omega of t, think of it as the solution, the flow of the Euler equation on omega 0, and this just takes C alpha to C alpha. But you can sort of exit that space in infinite time. So you can lose all regularity in this space. At least you can lose it up to this quantitative rate at which you do it. And this rate is sharp, so famous work by Vladimir Shverak and Sasha Kiselev. shows that there exist examples. I think the domain is a disk nearby certain steady states, which show that there's data for which this double exponential bound is saturated. So indeed, you not only can you, but you do lose all regularity in C alpha for some solutions. And this is a very natural thing because C alpha is measuring small scale filamentation that's happening. And if you've ever seen how a fluid moves, say, if you have some vortex, there's some differential rotation. The further you go out from the vortex, perhaps the slower you travel around. And that differential rotation induces filamentation, which is measured in C alpha is very big and grows without bounded time. Okay, so these function spaces C alpha are some way to quantify that and to say that that happens, but they're not necessarily a good way to give some picture of the motion at late times. There's another classical theorem, and this is by Udovich. And this says that for all bounded initial vorticity, there exists a unique bounded vorticity, weak solution of the Euler equation, such that, first of all, because the vorticity is transported, the solution in L infinity is just equal to its initial data, infinite for all t. This should be contrasted with this estimate. And two, the solution map, which takes L infinity to L infinity, is weakly star continuous. Meaning that if I have a sequence of initial data which is converging weak star to say some omega 0, weak star means I integrated against an L1 test function and those integrals converge. Then the solution operator for any finite time, weak star converges to the corresponding solution operator from omega 0. So this is saying that Euler, when posed for bounded vorticity, is a perfect dynamical system. In fact, a compact dynamical system. So you can think of, let's say X is a unit ball in L infinity. Euler is sending X to X for all t. And because Euler is time reversible, you get the full space X. So this is an equality for all time. Now, the issue that we'd like to discuss, and we don't have very much to say about this, but still we can sort of discuss it, is what happens at infinite time. And first, let me just say that you have to ask this question in sort of the appropriate way if you want to say something non-trivial about this long time limit. This is because, again, since Euler is time reversible, from any initial condition, so any given state you want in the L infinity ball, you can find an initial condition that reaches that state at a given time by time reversing the dynamics and starting there. So the typical way that omega limit sets are defined in dynamical systems is not really capturing the essence of the question of what's happening at infinite time. That omega limit set is really take the whole phase space and you look at its weak limit. Rather, I want to define, first of all, omega limit set, weak star omega limit set from a given datum to just be the intersection of, say, the weak star closure ST omega 0 T greater than S of the orbits. Okay, so because I have uniform boundedness in L infinity and vorticity, subsequences have convergent sequences have convergent subsequences in this weak star sense, and I want to collect all those weak limits from a given initial data along the orbit of an Euler solution, and I'll define that to be the omega limit set in this weak star sense. And now I want to say that, propose this definition of the omega limit set of this whole unit ball in L infinity, my phase space on which Euler forms this compact dynamical system, to be just a union over all points in that ball of this omega limit set. And I believe that this is a very reasonable object to consider for characterizing what we see at late times in 2D perfect fluid motion. And the question is, what's the structure of this set? So as I'll show you later, sort of all numerical evidence that we have points to the fact that over long times, any old initial condition will sort of generic points in this L infinity ball will start to look like some very particular types of configurations. Evidence for this set being a meager subset of the full phase space X. And this decrease in diversity of end states is sort of like the opposite of the second law of thermodynamics for 2D Euler. Namely, instead of entropy increasing, there's some decrease of entropy corresponding to a selection of some very particular elements in X that you see at long time. Okay, so the mystery is to understand structure of omega plus and decrease of entropy. Okay, and I think this will be even more clear when I show you videos.
Maybe you comment just 1 second on why the other definition is
Yes.
not the right one to look at here.
The other definition, you look at the weak limit. So here I'm fixing initial data and I'm looking at the weak limit in time. The other definition, you look at the weak limit sort of the whole ball. So you can take simultaneously sequences of long time and initial conditions. In that context, then it's easy to show that that definition is the whole X itself. Okay. So let's begin. So okay, we're gonna just try to understand as much as we can about this set. Let's begin at the natural place, which is to understand fixed points. Okay, and let's start with some examples. So, okay, first, if you have a periodic channel, then any shear flow, which is some function of y times px, I should actually start at the beginning, which is the condition for a fixed point is that u is orthogonal to gradient of omega, and if you translate this at the level of the stream function, this says that the gradients of the stream function are parallel to gradients of omega. That's the condition to be a steady Euler solution. Examples of this are shear flows on the periodic channel. They have this property. On the disk, you have these radial flows. Again, have this property. And on a general domain, you can construct these things by demanding a functional relationship between the vorticity, which is the Laplacian of stream, and the stream. So if you just seek a solution of this semi-linear elliptic problem for a given prescribed f, any such solution will define for you a steady Euler solution on this whatever domain you like. This equation, which is supplied, by the way, with some constant boundary data, let's say 0. This equation is not always a good equation. It can have one, many, or no solutions. This is just easily seen by the eigenvalue problem if f is linear. But there exists a very natural class of f. So these are so-called Arnold stable. So these are f which satisfy that either the derivative is negative but bigger than minus the first eigenvalue of Laplacian or F is positive and bounded. There's type 1 and type 2, or type 2 and type 1 Arnold stability conditions. Under these conditions, you have solutions of this problem, and moreover, they are nonlinearly stable dynamically in L2 of vorticity. So such steady states are nonlinearly stable. As a remark, it's easy to show that all the Arnold stable steady states have to share the symmetry of their domain. Namely, if you have some killing field, if you have Euler on some domain with a metric and you have some vector field which is killing for that metric, which is also tangent to the boundary of the domain, then that field commutes with the solution. It's symmetric with respect to that. And so an example of this is all Arnold stable things in the periodic channel are shears, because the killing field is just d by dx. On the disk, they're radial, and on the general domain, well, either you don't have such symmetry or they have to conform to it. And so what this is kind of telling you is that the stable structures that exist as fixed points in these fluid equations see in some sense the large scale geometry of the setup, which is some partial reason why when you stir coffee it axisymmetrizes and so on, but only a partial reason. The underlying reason for that statement is that these Arnold stable things are actually minimizers of the energy on isovortical sheets. Isovortical sheets are just these orbits. So if you look at the Arnold stable solution would be such a thing for which if you look at its orbit in the group of area preserving diffeomorphisms, the energy would be either minimized or maximized. And that's the two different cases. Another remark about steady states is that they're not really steady. The velocity is time independent, but if you look at the particles, the physical composition of the fluid, the particles are generally in motion. So in fact, if you think about the shear flow, the particle up top is going much faster than the particle at the bottom. And so this one is making laps around this one as you run in time. So not only are the particles not stationary, but they're getting arbitrarily complex in a way as you go to long time. So it's like many wrappings are happening. And so this picture of stationary simple flow has a dual picture in the case of particle configurations, which is very far from stationary simple flow. Okay. Okay, so the next natural question of, I forgot to say, actually, no, I wanted to say, okay. Steady states for Euler come in just huge families. And the fact that they come in such large infinite dimensional families makes predicting the outcome of some perturbation of a steady state an incredibly difficult problem in general. So let me just quote one theorem about the plethora of steady states. So this is a theorem of Chapru. I won't state it precisely, but roughly, if you let M be an angular domain, and you consider omega 0 to be Arnold stable with some extra non-degeneracy conditions. In particular, it has no stagnation points. So it's like a shear flow on an annulus. You cut out the center. Then there's an epsilon such that for all omega, which are in a ball of radius epsilon around this steady state, And this ball, I think, can be in like C11 or something like that. So in some topology. So for all such vorticity functions in a ball around the steady state, there exists a unique new steady state, let's call it omega bar, which lies on the orbit of omega in the group of area preserving diffeomorphisms. So in a way, steady states are in a one-to-one correspondence with the distribution function of nearby vorticity fields around the steady state. And so this shows you how incredibly rich the local structure of steady states are nearby these Arnold stable things. And it makes sort of obvious the obstructions to trying to prove asymptotic stability to any one of them. I think in my last talk, I mentioned some result with Peter and Dan that was somehow analogous to this, but at the level of the stream function where you deform the domain. But this result really for these fixed domain and parameterizes these steady states by distribution function. It's an interesting question. I don't know if you can have any Euler steady state which is really isolated in some topology from other steady states. I'm not sure if that's known, but I think it'll be interesting to resolve that. Okay. So now we'd like to begin discussing what happens to perturbations of steady state. So if I have some kind of stationary configuration, maybe stable, maybe not, what happens if I just perturb it away from steady? And there are some results, not too many in this direction. Let me begin by just stating one due to Koch, and also slightly later by Margulis, and which says that any omega zero steady state whose Lagrangian flow is not time periodic. This is what I called in my last talk a fluid clock. So I discussed that a little bit. So whose Lagrangian flow is not time periodic, is non-linearly unstable in C alpha. And okay, I think the regularity here is actually C1 alpha and you can C alpha there. And so what this means is simply that for any namely for any epsilon and any m, there exists a t which depends on those two numbers, such that I can start within epsilon of that steady state, and by time capital T, the solution emanating from that initial point is m far away in C alpha from that steady state. And the proof of this is actually quite simple. It uses the fact that the stationary state experiences some of this differential rotation that I mentioned before. The fact that the Lagrangian flow map is not time periodic means that, well, okay, so let me just draw some domain and think of the levels of the stream as foliating that domain. So here's the domain, and these things are just levels of the stream function. The fact that it's not time periodic means that the period of revolution of a particle starting on some of these levels is not constant. And so in particular, if I connect them by a little extendable thread, then it will just grow in length indefinitely by the background steady state motion. Using this idea together with some argument involving some kind of stability, contradiction argument that I got, you can say that in fact, this by sort of localizing a perturbation to appear at some late time nearby a shearing region, you can find data which experiences as large as you like growth in C alpha because of this relative shearing from the background. And so this theorem is sort of the first step towards quantifying small scale filamentation nearby stationary solutions of 2D order, like I mentioned before here. Yeah.
What's the reason? I mean, so you asked that omega naught, or rather they asked that omega naught is in C1 alpha, but then their differences are only measured in C alpha.
Yeah, that's a kind of funny point. That's okay, that's my recollection of the statement, and I think it's used actually in the proof, but let me not comment too much about it now, but we can, yeah. So Udovich discussed these issues in great detail in various papers that he wrote, and he conjectured something stronger than this statement. Namely, he conjectured that for all, say, initial data, which is C alpha, there exists some nearby point, say, in a small ball around the initial data in C alpha, such that the solution emanating from that point grows without bound as t goes to infinity. So that you have sort of infinite instability or infinitely fine filamentation over time. And moreover, he said that, okay, at least this should be true, at least true near steady. And my interpretation of that is just that he thinks that near steady states, this statement should be perhaps easier to prove, but it really should be true for any point in the phase space that you have this type of indefinite growth for some nearby point. And there aren't very many results that really go into, or really can make statements for all time. I already mentioned one, the Kisselev-Schwarz proof that upper bound is sharp. But I think this started originally by work of Nadarashvili, which I'll talk about. And so Kisselev-Schwarz, Latosh, Elgindi, Jiang, Denisov. These are all people who have worked on this and have made contributions to making statements of this type. Generally speaking, as far as I understand, there's sort of two ingredients that go into making an all-time statement like this. One is stability of velocity, which is the vorticity, or
Yeah.
the vorticity.
W bar.
Oh, sorry, W bar. So this is, it's the solution starting from that point. Yeah. More question? So there are two ingredients that go into these type of all-time statements. One of them is stability of the velocity field. So you want to sort of start by some steady state which is stable. And this can either be by, I mean, this is generally accomplished by some sort of symmetry or onward stability. And then there's stability of the picture, which is the background steady state. Is you can sort of visualize what it's doing to a passive blob of particles that's affected by it. And you'd like to say that picture of what's happening persists for perturbations that are not steady. And this is usually accomplished by some kind of trapping or invariant sets. In the examples I know of, this is, for example, if you have boundaries, the fact that particles that start on the boundary can't have to stay on the boundary gives you such a invariant set which you can exploit to say something about that picture that you have in your head stays for perturbations. Okay, so let me tell you what our Philly's result. Are there any questions? Okay, so Nadarashvili proved actually a wandering statement. So it implies, and his proof implies this growth in C alpha, but he actually proves something somewhat distinct from that. Namely, he says there exists a point zeta, or in L infinity. Actually, it's smooth, but let's just say there exists a point in L infinity such that, and an epsilon, such that all omega 0, which are in all of radius epsilon of zeta in L infinity. Oh, and sorry, and a time. So there exists a point, an epsilon, and a time, such that all omega 0 that start within a ball of epsilon around zeta and L infinity satisfy that they are not in the ball of radius epsilon around zeta in L infinity for all times bigger than that prescribed one. So namely, you have a point in the phase space and a neighborhood of that phase space on which Euler is a perfect dynamical system. And this point is wandering in the sense that if you start there, then eventually you have to leave there for all later times. So this should be contrasted with results for finite dimensional volume preserving systems for which we have Poincare recurrence that say this happens with probability 0 in a way. So you can't have this. An implication of his result, or rather the proof of his result, is that in fact, if you look at the solution starting from any such omega 0 nearby, zeta and zeta itself, in fact, grows at least like t to the alpha in C alpha. So you have this infinite time growth in those spaces, but actually I think one of the beautiful parts of this statement is already just the wandering in L infinity, which is not implied by this. Okay. So how does his argument work? Well, it follows those two ingredients that I said. So who is this zeta? He works on the annulus, but let's work on the periodic channel. It's really the same. And let's take Couette flow. So V is y comma 0. And let's define zeta to be Couette flow plus a little smooth bump supported on a line connecting the top and bottom boundary. So zeta is V, well, zeta is the vorticity. So the vorticity of this is -1. So of Couette is -1. So zeta is that vorticity plus this bump. And now, so why is it wandering? Well, first of all, Couette flow is non-linearly stable for Euler and L infinity, vorticity, in fact. In particular, it's non-linear stable in L infinity of velocity. I mean, at least it implies that the L infinity norm of the velocity stays close to its initial data for all time. This is a small perturbation of Couette flow, which means if the velocity is 1 here and 0 here initially just for Couette, then it remains bigger than 3/4 here and less than 1/4 here for all later times. So there's always a relative velocity pointwise on the boundary under evolution for any such perturbation, in particular for this one, by choosing things suitably small. That means that if you look at the image of that line underneath the flow, it starts to develop this sort of barbershop pole character. This is L of T. You know it has to do that just because this one is lapping around that one at least like some factor of T. The wandering comes from the fact that since zeta is this plus coet, in particular, this line here has no support on that side of the channel at the initial time. You can sort of leave a small ball of that in L infinity as soon as this line, which carries some value of vorticity, intersects this side of the channel for all later times, because such a state would be far from that one in this sense in L infinity. And that has to happen here because of this relative motion of the top and bottom. So you're always intersecting this side of the torus at later times, at some fixed later time, depending just on the size of the perturbation and so on. And so that's the wandering. The growth in C alpha can also be obtained from a very similar setup to this. Actually, I don't know exactly how to show it from this data, but you can take another data which is similar, involving two lines, and then you can show that the distance between these two lines has to go to 0, at least like 1/t, and that gives you C alpha if these are carrying different vorticities. Okay.
So Theo,
Yeah.
you mentioned the connection to Poincare recurrence, right? Or
Yes.
But I mean, there's a statement about Poincare recurrence just for general measure preserving systems. In this case, it would suggest that if you have this wandering, that there's no finite measure on L infinity that's preserved by the system. Because otherwise, then I think it would imply that you have recurrence.
Sounds reasonable, yeah. But maybe, I mean, you could have a measure which is like on a steady state. Couldn't you?
That's true. Yeah, okay.
I don't know exactly how to interpret
Yeah,
that.
with I guess something about supported measure.
Yeah,
That can't be supported on balls.
yes. Yeah. Okay, so in sort of the spirit of, so this is for a particular flow on the channel. So in the spirit of Udovich's question, so this is together with Tarek. We have some generalization of these type of ideas, actually not the wandering, but the growth in L infinity. So we consider any domain and certain class of steady states on that domain. These steady states are stable in L2, and they have and sort of they're monotone in the stream function near global max or min. So what I mean, so like if I look at this steady state and it streamlines, the vorticity is constant on these streamlines. And if the vorticity takes its maximum value, say at the boundary or at the center, and the vorticity varies strictly monotonely in a neighborhood of those points, so monotone decreasing or increasing in a neighborhood of those points, then those are the steady states we consider. For example, they could be radially decreasing vortices on the disk. Monotone shear on the channel. So, for example, Poisson flow, which has vorticity, which is just y, the vertical coordinate. So any such steady state, we can say that the set, let's call it d epsilon omega 0, which is the set of omega in a ball of radius epsilon around that steady state in C alpha, such that the corresponding solution in C alpha grows at least like T to the alpha. So the set of points in that neighborhood which have this growth, like Nadarashvili shows, this is open and dense. In the ball. So in a way, it's saying that this long-time filamentation that's established in these contexts is really a generic feature, at least nearby a certain class, rather large class of stable stationary states. And I won't go into the proof, but I'll just say that we use this monotonicity of the background vorticity as a function of the streamline to essentially get a different type of trapping mechanism. Because if you have vorticity which is varying strictly monotonely in some region and you know L2 stability, it's saying that the particles carrying those vorticities can't really go very much through that region, otherwise the L2 stability would be violated. So instead of using like two boundaries the way Nadarashvili did, you can use a region of such monotonely varying vorticity to say that the picture remains stable there. And because the picture remains stable, you can show this type of infinite time growth. Okay. So this is in the direction of Udovich, but still very far from the statement that he really wants to show. Any questions? So I kind of view these types of statements as telling you that the Lagrangian flow map is getting increasingly complex, because the real mechanism for this type of C alpha growth is just the fact that the background Lagrangian flow is twisting. And so you're seeing growth like to the alpha is essentially a measurement of this twist of the background flow map. I'd like to now, in the remaining time, talk about a sort of dual picture, which is at the level of the vorticity field. Just what does the vorticity field look like? Namely, rather than measuring it in some strong norm, which is detecting this filamentation, what if we sort of took our glasses off and looked at it in a coarse grain sense, which is what this weak star limit is capturing? So what does that vorticity field look like? And let me start with an example, which is just linear transport. So suppose I have a scalar field theta, which is moving by divergence-free velocity field u, which is autonomous. So time independent, given by some Hamiltonian, given by some stream function in 2 dimensions. So this might look something like this picture I always draw. So a lemma about this system is that if u is not isochronal, namely if the period of revolution on the different streamlines is not constant, then there exists initial data, namely the initial data that has support along streamlines of non-constant period of rotation, such that the corresponding solution in C alpha grows like T to the alpha, just like in these previous results, showing that it's essentially a linear mechanism by this differential rotation that causes that growth. And moreover, the solution converges weakly to the projection onto functions of the stream function of its initial data. So you have this weak averaging of the value of the initial data on the streamlines. That's the picture that emerges at late time for the scalar field. So these are the type of dual pictures. I mean, this one is telling you that picture of the filamentation. This one is telling you that things on average are starting to look like some simpler thing where you forget a lot of the details of the initial data. I mean, this average value is just integration on streamlines of the initial condition. So in particular, if you look at the omega limit set of the whole unit ball, say in L infinity, again, this system is sending the ball to itself and it's reversible. So if I look at the omega limit set of that whole ball, as I define it over there, this is actually just the projection onto functions of psi of the ball. So you have this dramatic reduction in the types of states that you can see at the end, which are just those that are sort of functions of one variable secretly, where that variable is the stream function. And the mechanism here for this decrease of entropy is that you have a preferred direction and you have some anisotropy in the system, which is that I have a particular autonomous field that I'm moving the scalar by. So in the end, I see a property of that field, and that's just represented by this. For Euler, it's much more mysterious because there's no, at least in general, there's no privileged structure that you should definitively see unless you start nearby something stable. But from the point of view of the whole ball, there's sort of no obvious selection of some special things. Okay, so finally, let's discuss, so what about Euler? Again, our aim is to understand this set. One major distinction between the passive scalar case and the full Euler equation is the additional invariant, the kinetic energy. So the scalar has all the same Casimirs as the Euler does for vorticity, namely any function of theta is preserved, but it doesn't have an analog of the kinetic energy. And the kinetic energy is a quantity which is weakly star continuous. Namely, if omega t is weakly converging as time goes to infinity on some subsequence to omega bar, then the energy associated to omega bar is equal to the energy associated to omega 0. Namely, you don't lose any energy at infinite time because the energy is one derivative smoother than the vorticity. On the other hand, the Casimirs can be lost, right? Because these are not continuous in this sense. Namely, if I have, for example, F strictly convex, then the integral of F on omega t is bigger or equal, and this is equal to the integral on F on omega 0. This is bigger or equal than the integral on the weak limit by lower semi-continuity. So you could, in principle, lose some of this Casimir on infinite time limits. So maybe said more simply, if F is x squared, this is just the entropy. And this is saying that at infinite time, you can lose entropy. This is mixing. Okay, so it's saying mixing is occurring. So we already saw that here, right? Because if I take initial data theta 0, which happens to have, say, mean 0 on the streamlines, then I'm saying this is weakly converging to 0. So you lose L2 norm, obviously, in the limit. And that can happen in general, and it can happen for Euler. Okay, so these are kind of the immediate constraints that we know about what the structure of any long time limit has to be. And from it, we can begin to just speculate what long time limits look like generically. So there's a couple of sort of theories in this direction. And I'm not going to talk about this at all, but there's a whole field of statistical hydrodynamics that in a way specializes at making this type of prediction by some principled deduction. Let me just mention here a theory of Crankman, which I think is also called selective decay theory, which says that the long time behavior, say omega bar, should generally be should maximize mixing defined by minimizing entropy, subject to having constant energy. Okay, and if you take this seriously, then you get the prediction that the long time behavior should be things on the first shell of the Laplacian, which is interesting because these things are essentially the largest scale structures that exist on your domain. So for example, on the torus, these are things like sine x and sine y. On the disk are the first radial functions. And so in a way, I think this was in fact part of the motivation for the inverse cascade idea that he had, that in 2D energy propagates from small scales to large scales, because under these hypotheses, you find that the state that you go to should be essentially the largest scale available. Of course, you can't take it exactly literally because it's easy to see that this can't always be true. There are initial data for which you can really definitively say you don't go to something like this, but it's a reasonable thing to build a theory on, and it seems to capture some of what's going on. One point that's a little bit unsatisfactory is that you are defining maximizing mixing by minimizing one particular Casimir, the entropy, the L2 norm of the vorticity, where you could really choose any convex Casimir and you could make the same statement and the prediction would change, in fact. So that's sort of a sticky point about it. And sort of in this direction, there's a paper by Schnellman, lattice theory, I think is in the title, where he essentially generalizes this idea in a way. Let me just quickly explain his idea. So he says, rather than pick a certain Casimir and maximally maximize the mixing defined by minimizing that Casimir, he says, let me give you an objective notion of this. Let's take this orbit that we discussed of a given initial condition, and then let's look at the closure of this orbit, weak star and L infinity. So these are all the vorticity fields that can arise by mixing of the initial one. Now, to get closer to the Euler equation, let's intersect this set with those vorticity fields that have energy equal to a given one corresponding to omega 0. So now we remove the irrelevant ones that don't conserve energy. This set, by the way, of course, contains the omega limit set from that given initial data. So at least the Euler thing is living in this set, but of course it doesn't have to be that set, and in general it won't be that set. Nevertheless, what Schnellman proved, let's call this thing Y. Schnellman proved that for all omega 0 and L infinity, there exists an omega bar in Y which is steady. Namely, there is some mixing of any initial vorticity which is bounded that has the same energy of that initial vorticity, which is a steady state for Euler. And moreover, it has the property that Laplacian of the stream function is equal to f of the stream function, which is the vorticity. So it has a monotone f, like the beginning that I talked about, and this f is a monotone function, not necessarily strictly monotone, but a monotone function. it's what it's saying is that at least based on the considerations of energy conservation and mixing, you cannot rule out convergence towards a steady state. Maybe can I take like 10 minutes?
Yeah.
So in some recent joint work with Michele Dolce, we sort of revisited these ideas. We made some additional statement about the structure of these guys, but also we give an example where you can definitively rule out convergence towards some type of equilibrium. Namely, we say, you know, given any, say, shear flow, that's not important for the statement, but conceptually it's nice. So say given any shear flow on the periodic channel, there exists a nearby point in L1. So there exists a Xi, which is smooth, such that Xi is close to that shear flow in L1, for which the solution starting from that Xi cannot converge weakly to a shear. Any shear. So if you're familiar with the results of inviscid damping that I'll talk about at the very end just briefly, this is saying that you can't have convergence to the symmetric equilibria on the channel. And the idea of this is just very simple. So if you have a channel and some shear on the channel like that, this Xi is just that shear flow plus a very localized approximate point vortex. From smooth but approximate point vortex, say of radius epsilon. And the point is that the energy of such a thing is like log epsilon. But using the ideas of Schroman and how to characterize the weak star closure of this set, you can show that any sort of rearrangement that lies in this set that is a shear flow have order 1 energy. So because energy is weak star continuous, there's no possible way for you to take an approximate point vortex and redistribute it into a shear. Okay, that's the whole idea. Okay, so that's saying at least what it may not be in some case. What about what it is? And I'll end here and then I'll show some videos to. Actually, can I show the videos now? Yeah. Okay. So this is my YouTube channel. Okay. So first of all, this is sort of irrelevant. This is more to the regarding the theorem with Tarek. So the theorem applies to such a thing on the two torus periodic at the two sides. It's nearby sine x sine y, which is by itself not stable. But if you look at odd perturbations, which this one was, it is nonlinearly stable. And you can see that what's happening here is just that these things are filamenting and the growth is indeed like T to the alpha, I mean, in this region. So, okay, that's the type of stable filamentation that I was talking about before.
There's some of this advantage.
Yeah, well, I don't know how to show that, but. Yeah. Okay, now this is pertinent to what I was saying now. Take any old data. This is just Gaussian random field that I give at the initial time. That's the stream function. And then I let it go under slightly viscous, but essentially inviscid flow. And you can see the picture that I guess you've all seen before of like sign vortices merging in some kind of stepwise process until big ones are formed. And at the same time, I'll go to the end. what you see in the end is a real ordered structure of vortex dipole with some satellites that may or may not fall into them at late times. I don't know. If you do the simulation again and again, you'll see a very similar picture. Sort of every time you see something very similar to this. There's one that I like to show. So I did these simulations like for a summer, every day I did a simulation, and one of them looked like something kind of different. This one at late time, instead of the dipole emerging, you have a dipole of tripoles. But nevertheless, the end state is much simpler than the beginning. And that's a general feature that you see over and over again. So what defines this? So there's a conjecture by Schroeder about the structure of these end states, or about a characterization of these end states. In the language that we discuss in this talk, the conjecture is that omega, the omega limit set of the unit ball in L infinity consists of exactly all omega 0 in that ball, such that the solution starting from omega 0 all time is pre-compact in L2. Namely, it's the initial data which don't experience mixing at infinite time. So an example of this are steady states, time periodic things, quasi-periodic things. It could be more. But okay, we don't in general know how to characterize this set. But moreover, and this is something I learned from Schreck, those initial data, or sort of generic initial data, should give rise to orbits which are not pre-compact. Namely, generic initial data should experience some mixing at infinite time. And indeed, when you look at these videos, you see that because when these vortices are emerging and you form these bigger ones, they have some differential shearing, and that shearing is mixing the vorticity around it, and that should give rise to some kind of loss of L2 norm, say at the infinite time limit. So it seemed very reasonable. Both of these statements to me seem very reasonable. And it would quantify decrease of entropy. Because you're saying that the non-generic set, this meager set of L2 pre-compact orbits, is exactly the things that you see at long time. As far as I know, this is completely open, so it's not even proved that this set is not the full set X, but strongly believe that's true. I would like to just end with a further conjecture by Klaas Moden, which not only tells you that there should be a decrease of entropy, but tells you what a generic element of this set should look like. And I'm going to show you some videos. So Klaas Moden says that generically, elements of this omega limit set should behave as point vortex solutions with largest number of vortices which are generally integrable, for which system is generally integrable. Okay, so let's just see the final two things are just some verification. So here the simulations are done on the sphere, and it's using Zeitlin's model, which is a better way to discretize the fluid equations than what I use, which is just Galerkin. So this carries more of the Casimir information at the finite level. And what he sees here is that over long time, you see 3 vortices. And it turns out that for general data, without any additional structure on the point vortices, 3 is the largest number for which that system is integrable on the sphere. Okay, so now let's test the hypothesis by considering data with vanishing angular momentum. Now, 4 vortices with that additional symmetry on the solution, 4 vortices are generally integrable. And indeed, what he sees is convergence at late time to 4 vortices. And apparently this is a robust feature across many simulations that he's done. And thus he conjectures that this is sort of the picture of the omega limit set. Okay.
Questions?
So,
Go ahead.
no, so I was speculating, the reason for the integrability is that after it's integrable,
Yeah.
it settles down and there's no
Yeah.
chaotic behavior anymore, so that you can't do anything else with it.
I think that's very reasonable. The question is really, how do you organize into those integrable, how do you start to look like those integrable point vortices? That I guess is completely not understood. But once you start to look like that, it makes sense that you shouldn't be able to look like a non-integrable one. It should be the integrable one.
So there are probably many non-generic, say, quasi-periodic solutions.
Yeah, definitely. Yeah, definitely. I sort of hope that dipole of tripoles is exactly one such. I think it's probably not generally stable, but maybe something like that really exists.
It's funny, like stumbling on a non-generic solution.
Well, it could be sort of, yeah, okay.
How many times have you tried before you see the dipole?
I don't know, maybe like 50 or something.
So they really seems to be stable in the end,
Yeah, the dipole itself is interesting because on the plane, equilateral triangle of equal sign vortices, like sign vortices is Lyapunov stable, and the dipole itself is Lyapunov stable. So it's like the sum of 2 Lyapunov stable point vortex states. So there is some stability you might imagine that the dipole of tripoles could have from point vortices. And then that you can desingularize into an Euler solution is, of course, non-trivial thing, but it's not unreasonable. It could also be metastable and it could disappear at some point, but yeah.
These in the end are also not point vortices. They're made up of tons of tiny little vortices, etc.
That's true.
In that sense, the tripole is also.
Oh, yeah, that's true. But the interesting thing in his paper, he actually uses the point vortex trajectories and compares them to these, and they match very well. So
It's great.
it's remarkable, but yeah.
Okay, there does not seem to be any other questions, so thanks.